This is the second in a series of videos on probability. And let's review real quick about the terms that you need to make sure to know. If not, go back to part one and make sure you understand them. And that is we have the concept of an experiment, the concept of an outcome, of an event, and of a sample space. And the key here is the relationship between outcome and event, and also the sample space is the listing of all outcomes. So once we have that, we have another concept, the key concept, and the key concept is ELO. Or equally likely outcomes. But rather than say it all the time, I'll just say ELO. So equally likely outcomes. And it turns out that probability is very easy when there's equally likely outcomes and more difficult when there's not. And so a lot of times we rewrite problems so that they're specifically ELO problems. And let's look at a definition. We say an experiment is ELO, or has equally likely outcomes, if all outcomes, if and only if, all outcomes are equally likely. And let's look at an example of something that's equally likely. And then we'll look at something that's not. So let's do experiment number one. Experiment number one is you roll a single die. So the sample space, let's call that experiment A. So the sample space would be A, 1, 2, 3, 4, 5, 6. And then the question is this an ELO experiment or not? Well, the way you have to know that is you have to think about your die that you have, right? Draw that real quick. You have to think, if you roll this die, are all the outcomes equally likely? There's 6 outcomes. It turns out that with a die it is. All these events are equally likely. So this is ELO. And what's easy about that is that the probability of any one event, so the probability, say, that you roll a 5, is equal to 1 out of 6. And even though that's just common sense, we're going to use this easy problem to define some rules and terms, and we use it more complicated. So here's the definition. So if an experiment is ELO, then the probability of event A is equal to the number of times A occurs over the number of outcomes in the sample space. And that's where we got the probability of A. With the probability of rolling a 6 was simply the probability of rolling probability of rolling 5. The probability of rolling 5 was 1 over 6 because there's 6 outcomes in the sample space, and one of those was a 5. Let's say what the probability of rolling an even number was. Well, there's, again, 6 different possibilities in the sample space. The sample space is 1, 2, 3, 4, 5, or 6. So there's 6 possibilities. And you think, how many are even? Well, the 2 is even, the 4 is even, and the 6 is even. So that's 3 out of 6, or 1/2, or 50%. That's all the same. Let's think of a deck of cards. A deck of cards, the sample space has 52 outcomes. And they're all equally likely. So you can think about what's the probability that you get an ace. Since they're ELO, then the denominator will be 52, right? That's the total number of outcomes in the sample space. And on top here would be the probability you get ace. So how many aces are in a deck? There's 4. So it would be 4 out of 52. And you could do a more complicated problem. What's the probability that you get, let's say that you get a black, let's say that the probability that you get a face card. Again, the experiment here is you have a deck of cards, you draw on a single card. So that's an ELO experiment. So the denominator here will be 52, and to find the face card, you simply count up the number of face cards. Well, the number of face cards, you have a jack, a queen, and a king, but you have 4 suits, you have 4 of each of these, so that's 4, 8, 12, so it's 12 out of 52. Let's look at a problem that's not ELO, and we won't actually solve that problem, but we'll solve that problem the next time. In the next case, let's say you roll 2 die. And you add the faces. I guess you roll 2 dice, that's the plural. You roll 2 dice, you add the faces. So your outcome, let's call this experiment B. Your outcome here is you could get a 2, you could get a 3, a 4, all the way to a 12. And this is not ELO. Now there's 2 ways to do this. You can either do what's called a probability distribution function, or what you can do is you can simply reformulate the problem so that it is an ELO problem. But for now, the important thing to realize is that you cannot apply this theorem here because this is not an ELO problem. So that's the end of part 2. In the next video, we'll go into more detail into similar problems.